Good morning, everyone. At the moment, we're at a great stage within the container revolution. It's getting all of the excitement and everyone's enthusiastic about it. But what we're also seeing is how it can actually start working and how it can actually start working and adding value to our companies and to projects in production and delivering back on the promise of how these containers can deliver great, amazing things. And this is kind of what I want to go into today. I want to talk about how we can actually take containers, remove some of the buzz and buzzwords and excitement, and actually get down to how do we start delivering value and how do we start adding and supporting containers in production and at scale using toolings like Kubernetes. So my name is Ben Hall. I am the founder of a company called Katacoda, and Katacoda is an interactive learning platform for software developers. We give free hands-on interactive tutorials, and everything is in the browser. You don't have to download, you don't have to configure everything. And we have topics and content on Kubernetes, on Docker, on OpenShift, and we take you from getting started all the way up to running and scaling in production. And for today, what I want to start with is why I personally consider containers being important, why I'm so passionate and enthusiastic about them. And then I want to walk you through the process and some of the tips and some of the tricks that I've picked up about how you take it from building an ASP.NET Core application, running as containerized application, deploying that onto Kubernetes, explaining what Kubernetes is, and then using Azure to help scale that out, help run that in the cloud, and then explain some of the advantages, some of the benefits that Kubernetes can bring, and what problems it can solve. And so if we start and look at the ecosystem at the moment, we're in this really amazing explosion of technologies. We have awesome new languages which are appearing, such as ASP.NET, but also things like Elixir, F#, and some of the functional things are actually starting to become mainstream. And this is great, but also it becomes a problem, especially when we need to manage and maintain all of these different languages and all of the potential applications, all of the big data solutions, all of the NoSQL data storage offerings. And if we always have to reinvent the wheel, if we always have to figure out how we need to install, how we need to manage, how we need to back up, all of these interesting complexities start coming into play. And this can have a huge impact about how quickly we can innovate and how quickly we can start adopting these technologies. If we keep needing to learn everything every single time, and we need to change how production works and operates in order to support these technologies, then that's going to add barriers, that's going to add blockers, and it's just going to remove some of the advantages that they can bring. And then once everything's running, we still have to maintain it. We still have to worry about how do we do upgrades and how do we make sure that we don't have any downtime in the meantime. And so this is where I think containers can have huge advantage, because it can help simplify and help remove some of this complexity. It can help remove some of the uncertainties about how applications should operate and how an application should scale, what's required from an application in order to run effectively and properly and securely. And by having everything as a container, we introduce this standardization, where everything becomes a very consistent experience, from building applications using different languages to running and deploying them at scale and on top of technologies like Kubernetes. And I'm sure many of us have seen a container in operation. We have the Docker command line, and this allows us to go off to the Docker registry, which has got all of the Docker images. And these Docker images have everything which the application or the process needs in order to be able to start. It's got any operating system dependencies, it's got any runtime dependencies, such as the .NET Framework or the JVM, and it's got all the application configuration, the default configuration needed for the application to launch successfully. And this allows us to do things like Docker run, give it the image name which we're interested in this case Redis, the particular version, so we're not just using the latest, greatest, we're actually being very targeted, because the latest tag is amazing for those who have seen it. Like you just do Docker run Redis, and it will pull down the latest version, and you get the latest and greatest version available. But once you start depending on this latest version, the problem is that can change. The latest tag is a moving target. And so one day you'll be running Redis version 3, and the next day you may be running Redis version 4. And that could introduce some unknown side effects. So when I run images, I always am very distinct and very concrete with what version I actually want to run, just so I don't get any unexpected side effects. And so in this case, it's 3.0.3. And to make that container accessible, I open up the port. So I make the port available on the host, 6379. So any traffic I send to that machine gets proxied and gets passed to the container running process. And now it's as if, from a development experience, as if I've got Redis installed on my local machine. And so I can use and interact with it as a development dependency without ever worrying about how that needs to be configured under the covers. And as this container technology gets adopted, we're seeing more interesting use cases and more complex applications starting to be containerized. So now, with some of the amazing work that the Microsoft team have done, SQL Server, the official full-blown SQL Server, runs on Linux. They've managed to migrate the Windows NT kernel into the Linux user space using things which I do not fully understand. It's some magic, but it seems to work very nicely, so congratulations to them. But it works on Linux, and you can execute all of the SQL commands and all of the operations that you would expect from SQL Server on Windows. But because we now have it on Linux, it means we can now run it effectively inside of containers. And so in this case, I'm launching the latest CTP of SQL Server 2017. And as it launches up, you can kind of see normal operations which you'd expect from SQL Server. It's creating the master, it's creating the model, we've got some tempdb initialization happening. And when we launch the container, we have to pass it certain environment variables because it's a big blown system. Things like we need to accept the end user license agreement. And so we need to pass that in as an environment variable. And we have to set an SA password, something super strong and secure, such as this beautiful password of mine. But the benefit, as we can see, is this is everything which is required to run SQL Server. We don't have to download huge, massive installation files and ISOs anymore. We don't have to sit there and going through 10, 15 different screens and ticking boxes which we're not quite confident if that's a box which we ticked last time we tried to install it, or if it's the same configuration my colleague next to me has. And so now this container has introduced this standardization about what SQL Server looks like and how SQL Server operates. And of course, we can go in and we can tweak and modify and add all the extensions which we want, but we've got this consistent baseline to be starting with. And because we don't have to go through the installation, this is where things like the accept end user license agreement becomes a little bit different. Because like, how do you tick that box to verify that actually I do agree to these terms? And so this is where you see things like the old way of working and the traditional way kind of being exposed in a containerized system. And so this SQL Server started from an image. There's millions of images available on the Docker Hub. And these can either be used as kind of like foundation, and you can start those containers and run them within your systems. Or you can take and embrace and extend mentality. You can use these as the foundations for what your application looks like and what your application desires. In this case, things like the .NET Core. And then use that as the foundation to deploy your application on top of. And all of these images are based on layers. And this is a really important concept within the Docker system. Because when we deploy our application, and it depends on .NET, we don't want to have to deploy its own unique version of .NET every single time. If we're running 100, 200 different services, if they all had their own installation of .NET, that would just become a maintenance nightmare. And also, we'd need much bigger disks and much bigger hard drive space, and it would become much slower on the network, and everything would just eventually grind to a halt. And we couldn't do anything apart from wait for the .NET framework to be downloaded. And that's not very motivational, and it's not very productive. So instead, by having it as a layer, we can actually start reusing and repurposing the files underneath. They're all sandboxed, and all of the containers are completely separated for at runtime purposes. But in terms of the files on disk, they can share and they can reuse, and they can become much more effective in how they repurpose the different dependencies that they require. But from the application viewpoint, it's all the same. Everything gets flattened, and they just see the application hierarchy and this flat kind of merged file system. But under the covers, you've got the layers underneath. And now we've got these containers. And some of the benefits are they've got their own process space, so they can't interact and interfere with other applications which are running. They've got their own network interface, so you can open ports and send traffic to it. Their own root directories, so if you ask what's running inside of a container, it will have all of the files which you'd expect from a full virtual machine or a bare metal machine, such as user directories, bin directories, and Windows program files and System32, etc. But they're completely sandboxed and they're completely isolated. And so in many ways, they deliver some of the benefits which we would traditionally get from virtual machines, but containers are significantly not a virtual machine. They're much more lightweight. They're much more flexible, and you can get a lot more benefits from them in different ways. But for me, one of the main things is about the performance. Because we're not dependent on this hypervisor, which is managing the relationship between a guest operating system and our underlying host machine, we get all of the native performance. And in particular, we get the native I/O, which means that containers are great for running big data workloads, running SQL Server in the maximum performance possible, where traditionally VMs could have an overhead through that bottleneck and through that data path. But the other benefit is containers don't need a guest operating system. Containers operate against the host kernel and reuse and take advantage of what's already there. And so because we don't have a guest operating system, we don't need to wait 10 minutes for it to boot up. We don't need to pre-allocate a VM 8 gig of RAM in order just to run our node process in isolation. Instead, we can take advantage of the sandboxing and the nature without pre-allocating any hard disk or space or CPU, etc. And so what's actually running on our machine is actually what's required. And so we can get much better resource optimization and capacity planning about how our systems work. And because we don't have this pre-allocation step, everything takes milliseconds to launch. Docker is fundamentally just a process manager. It doesn't do anything apart from launch and secure processes. That's its responsibility. And that's all what's happening under the covers. It does this via kernel virtualization, and so when you run the process, it's taking advantage of the kernel from the host machine, and that gives it the performance and the capabilities under the covers. But there's three main concepts to keep in mind when you're thinking about Docker and you're thinking about the container processes. You've got the running process itself, which is the container. This process got launched by a Docker image, and you can think of this as like a layered zip file. If you exported a container image, it would be exported as zip, and that zip would just have multiple folders inside of it, each reflecting the layer under the covers. And then you've got the Docker registry, which can be public and hosted on the cloud, or it can be private and hosted inside your data center, which we'll look at in a moment. But it's important to remember that Docker isn't the only game in town. Docker isn't the only container runtime. We've got some really exciting technologies such as the container runtime interface as part of Kubernetes. We've got runc, which is a really low-level way of starting containers. We've got containerd and Rocket. And they've all got their slight opinions and their slight variations and some of the different advantages that they bring to the party. But they are all cohering and working towards a common standard. And that allows us to try and move around and experiment with different technologies and repurposing and reusing the same images under the covers. And so we've got the container runtime, we've got the Open Container Initiative, and that defines specifications. So the runtime spec, which is actually how do you start containers and how do you talk about them, and the image specification, which is how do you build an image and what does an image look like. And so we can have different technologies which all build and all go into this overall system. And this is what allows us to do things like run SQL Server in a consistent, reliable way. We start our container based on the image, and that's what brings up. But the containers aren't used just for background processes. We can also just use them for normal, everyday command line tooling too. And so when I work with Azure, I don't necessarily want the Azure command line installed on my laptop because I'm unsure about the dependencies it requires. My laptop at the moment is working quite happily, and I don't really want to mess with that. but I still want to take advantage of the tooling and I still want access to the Azure command line interface. And so now I can use all of this as a container. I can launch the container, I can pass this flag IT to make it interactive and work at the terminal, and then it works and operates in exactly the same way. I can set my credentials, I can launch and manage all of my Azure machines, and then when I'm done, I simply exit the container, and I'm back on my host, and everything is still exactly how I left it. And so now I don't get conflicts between things upgrading in the background which may have an impact on how I actually run my applications and how I actually do my daily development work. And all of these images are based on the hub, which I've mentioned, and they're all official. And so you can look at 90% of your dependencies, I'm sure, have an image already available, and you can take that and you can start that. Or you can simply use it as inspiration and build your own container and configure it how you need. And these images are great. They give a lot of value and means that we don't have to worry about dependencies. But what about our own applications? Well, how do we deploy and how do we build our own applications using containers? So what I've got is an amazing application built with ASP.NET Core, and it's got 2 classes. And this is the fundamental things required. The first program file, I'm sure many of us have seen if we've been experimenting with ASP.NET Core, but it's bootstrapping that self-hosting HTTP server. And the most important bit is we're defining the URL which we want to listen on. By default, sometimes applications like to listen on 172.0.0.1, which means it will only respond to traffic from the same network interface, i.e. localhost. But when you're in a container and running in a containerized world, only listening to localhost doesn't really help you because nothing else is running inside that container, which means you will not listen to anything apart from your own messages, which doesn't really help you scale. And so when you launch applications, you need to be very explicit and make sure that you're binding and listening to the outside world. And you do that by, in this case with ASP.NET, binding to 0000, so all of the IP addresses on the machine, and in this case, listen on port 5000, so we can respond and accept traffic. And then once a request comes in, no matter what request it is, we simply respond with the host name of that request, which in this case is also the host name maps to the container ID, because that's by default how it works in the covers. So this is our application, and this is what we'll be using now as our example. And now we need to turn it into a Docker image. A Docker image will then allow us to run it as a container and then allow us to deploy it onto Kubernetes. And so to start building these Docker images, we need a Docker file. This Docker file lives with your source code. It can be checked into your source code repositories such as Git, and it can be maintained and supported with the rest of your application. And the first part of the Docker file is defining what your application needs in order to be able to run effectively. So what dependencies does it require? So this could be Node version 6, Node version 8, or in this case, .NET 1.1.1. And because with .NET, we need the build tools. We need to be able to take our source code and build and compile the binaries, download the NuGet packages, and perform other things. And so we say that we need the SDK tooling as part of that. And this comes from the hub. There's different versions available depending on what you require. So if you want to go ahead and you want to start experimenting with the ASP.NET 2.0, there's an image available for that, and you can go ahead and download without worrying about how that will impact and how that will affect your machine. So the next stage is, once we've got our dependency, we just need to define how do we deploy our application. And thankfully, with the work which Microsoft are doing, it becomes a very standard, streamlined process, depending on, without too many switches between different variations in applications. So the first part is we need our application, and we need to give it somewhere to live. So we make an app directory, and we set that as a working directory. We then copy our CS prod file from our host machine, from our source code, and put it into the container and into the container image itself. And so now we can use that file in future commands, such as running .NET Restore. And so they'll go ahead, when that gets executed, it will download all the NuGet packages and all the versions that have been defined in the project file. And so we now have that foundation for what the application needs. The next stage is we need the application itself. And then we need to build and publish the binaries as a result. The reason I split these two is quite important. Because we don't really want, for every single build, we don't want to have to go back to NuGet and download all the packages if nothing's changed. If our CS prod file lists exactly the same dependencies and the same versions as what it was the last time we built the container, then nothing should have changed. Everything should be identical. So having to go back and download that maybe 5 meg or maybe 50 meg of dependencies, it's just going to add a lot of time to your build process, and it's just a lot of overhead which you don't need. And so as part of this process, Docker has caching built in. And so Docker is aware of the files and their versions and if they have changed or not. And so when we do this copy, if that file hasn't changed, Docker will just refer back to the cache and use the cached version of the run commands from the previous build. And so in this case, if the project hasn't changed, .NET Restore will just use the cached version. And so we don't have to go off and re-download our dependencies. So we get much quicker build time. Our application source code is likely to have changed. And so that will invalidate the cache on the next line. And as such, it will then rerun and re-execute the run instruction. As such, we get newly built compiled binaries as a result. And these kind of structuring and thinking can have a huge impact on build times, especially as you start scaling out to different projects and different approaches. So our application will now define how we build. We simply now need to say how to execute and what is the metadata around our containers. So what ports does our container listen on, and how does that application start in the first place? And by defining this within the image, this gives you that standardization and that standard way of launching containers without worrying about what technology it is on the inside. If every time we got an image which we needed to deploy, the first step was we needed to look inside and figure out what technology it was, and then look up how we actually launch it, that's going to add a lot of overhead, and that's going to start adding manual interventions or require scripting and automation. By having it baked into the image, all of the information which we need to launch is there. And so we don't have to go off and think about how that works and how that operates. So we've got this Docker file. It lists our dependencies. So we need to build and run that. And so when we do Docker build, we give it a nice friendly name of catacoda.net example. We give it our version number so we know what build we're actually referring to, and we know what build we want to push out, in this case V1. And then Docker will run through every single step in our Docker file, execute the commands, and we will eventually get our build image, which has got everything our application needs, so the .NET framework, it's got all of our NuGet packages and our built binaries as a result. And then that launches in exactly the same way that we was running things like Redis or SQL Server. This is the advantages that having this standardization and this consistent way of launching and starting containers really add value. Because whether it's a .NET application, whether it's a Node application, whether it's an F# application, we still have this consistent experience from the outside and a consistent way of managing them. And this really simplifies the build pipeline too, because we don't need our build agent to do anything apart from know how to communicate with Docker and how to run Docker build. The build agents don't need to be configured with particular versions or particular frameworks. We don't need to start ring-fencing build agents to run that legacy application which hasn't been touched, but we need to be able to build and release it, and it runs on a particular old version of .NET, which nothing else does. That can all be encapsulated and defined by the Docker file. And when you build the Docker image, all of that processing, all of that version is happening within containers itself. So our CI/CD pipeline just communicates with Docker now, calling things like Docker build, Docker run to run our unit tests and verify that everything happened successfully. And we'll start to see these consistent experiences. This is how we define Node. We still see the same pattern, defining our base dependencies, copying over our package JSON to define what our dependencies are, installing and building and running in that consistent way. But one thing you'll see is these images start to get quite large, especially now we've built our .NET application, but it's also included all of our SDK tooling. Now, this is great from a build point of view, but it exposes a security risk when we're running in production, because we don't necessarily want a GCC compiler on our production servers. Because if anyone did manage to find an exploit, they'd have all of the tooling which they need in order to download source code, compile it, and run it, and launch it on our systems. So Docker has realized this, and they've now corrected it, and added this concept of multi-stage builds. And this allows us to take our existing Docker file, which we all know and love. This will build our dependencies on applications, but as a side effect, it's quite large, like roughly 900 meg, and we can improve it. And so we can take a Docker file and combine that with something which is much more streamlined. And so we can add this second stage to the process. And the second stage is a way to optimize how we want our container to be built and operating and running in production. So we've defined a second base image. In this case, we only need the runtime dependencies of .NET in order to launch. So this has been cut down all of that additional risk and all of that additional attack vector because we don't have the build toolings in there. Again, we define things like working directories and how that container image launches. And then when we need our binary, we can copy it from the first stage. The first stage, which had all of the build toolings and can produce everything and create this out directory, we can copy that from the first stage into the second stage. And that is what we'll launch, and that's what we push into production. And as a result, what you'll see is you'll take a 900 meg Docker image, which has got everything, and that can be cut down and can be streamlined to something which is still on the large side, but it's a lot more streamlined, a lot more performant, a lot more easier to deploy into production at 250 meg, roughly. And we'll see that now, because how do you operate and how do you start pushing these things into production? Now we've got our image built and we're ready and we want to scale out. So the first thing is it needs to go somewhere. It needs, in order to be from a build agent or from your dev machine and pushed into somewhere that is accessible from production. And so you do this using Docker push. Docker push will push it into a registry. The registry, which is where all of the images are stored. And so in this case, it's pushing into the public registry and making the image available publicly. Great for open source projects or community ideas which you want to share and make them easy to deploy. One important thing to notice is it only pushes the layers which our application have changed. And this is where that layered file system really starts to take into account and benefit. We don't need to push the entire .NET framework because it's already on the registry. That's where it came from. And so Docker is aware of this, it checks to make sure, and so only pushing the 14 meg, which is our application and our dependencies, and everything else is just taken care of from what became before it. And when we do new builds and we create new versions, we'll push those in, giving them a different version name, and again, it will only push the layers which have changed. So that's where we can get a lot of value from having these optimized settings. And if you go into the public registry, go into Katacoda, you'll see the beautiful application running on the system. And from a build CI/CD pipeline, we kind of walk through these steps. We went from Docker build, which created the images, and then when we started the release process, that involved a Docker push. And then when we went to our servers, we'd do a Docker pull, which would download everything and make it available for deploy. But the public registry isn't very good for companies. It's not very good because we don't really want to release our source code into the open world. And so this is where you have hosted private registries. You can download them and run them locally on your machine, or you can use things like Azure and let Azure and Microsoft manage and make the registry available for you. So the container registry is very cool, it's very easy to work with, and it fits natively and naturally into the rest of Azure. So when you go into the portal, and it asks you a few questions, mainly what URL would you like, what DNS name would you like, and where would you like the location of your images to be. So whichever data centers you're particularly used to deploying to. And then you create the registry, and then you'll get given the DNS name, which you selected, in this case, Katacoda Demo Reg 1, bit of a weird name, but it seems to work. You'll then have a login, a username, and a password. And so this allows us to, from our command line, log in to the registry using the DNS which we entered, using the username and our super long, super secure password which Azure provided for us. So now we have this Azure Container Registry, which is private, and only people which we've explicitly given access to can access our images. And so in order to push our images, we need to tell that image where to go and where that image should live. And so by default, it goes to the public registry, which is docker.io, but we can change that, and we can prefix the image name with a particular registry URL, in this case our private one on Azure, and when we do a Docker push, it will now push into that private registry using the authentication tokens which we just logged in. And then the image is available, and we can see it in the UI, and that's now our process. So we now have it in Azure. So now we need to deploy. And this is where Kubernetes and complexity starts to be introduced. Because going to every single machine in your cluster and running Docker run isn't the most effective way of deploying applications. This can introduce a lot of uncertainty, it introduces a lot of manual processing, and it introduces a lot of risk. So we need a way in order to encapsulate that risk and reduce it and have a more streamlined, automated way of processing, running it. And this is where container orchestration comes in. There's many different orchestrations, so you may have heard of things like Docker Swarm, which is Docker's native one, things like DCOS, things like Kubernetes. And their responsibility is making sure that your containers are running in a healthy, reliable, consistent way across multiple different machines, and allowing them and enabling them all to communicate and act if you have one big compute plane and making that work. And so let's look at what that actually looks like in reality. So one of my personal favorite technologies is Kubernetes. Kubernetes defines itself as an open source system for automating deployment, scaling, and management of containerized applications. So it's kind of solving our production level problems and making it easier for us to manage our applications which we have just built. And Kubernetes was born from inside of the lessons which Google have learned. Google had been running containers for the last 10 years. They've run everything from databases to their big data workloads, to their search engines, to Gmail, to Maps. Everything inside of Google runs as a container. And you can imagine at Google scale, they have built some really interesting, really unique ways of managing this across like 40,000 different data centers and however many machines they have now. And this system was called Borg. And so Borg is how Google runs containers. And they produce a white paper which define how they operate and some of the lessons which they've learned and how they actually manage that in reality. And while white papers are really interesting to read, they're not as easy to implement in reality. You have to do a lot of effort to go from a white paper to have something running. And so in order to be able to capture that and in order to be able to make an impact, Google decided to launch Kubernetes and start this open source project. And so they took the lessons which they've learned, they made it applicable to a wider audience and wider version applications and approaches, and then released it to the Linux Foundation under a new foundation called Cloud Native Foundation. And so it's not driven by Google. Google don't have an incentive to control it. They've just given all of the IP, all of the copyright, all of the responsibility to a third-party independent nature. And what this means is other vendors and other companies are much more willing to adopt and work with the foundation because they're not driving Google directly, they're driving the community as a whole. And so you see companies like Microsoft and Red Hat putting a lot of weight and a lot of effort into Kubernetes because it is a community-driven project and it has that approach. Google is still very much involved. If you go to the Google Cloud Platform and you say you want to run containers, under the covers is all Kubernetes that you're dealing with and that you're managing. And so Google is still very passionate, still very enthusiastic, and still a major driver behind the project. It's just that they've invited other people to the party, which is great from our point of view because we get to build on the shoulders of many amazing companies. And its responsibility is to take this ocean of containers. We have data lakes, so we may as well have oceans of containers too. And take all of these containers, they all come into Kubernetes, and Kubernetes' responsibility is figuring out what the best, most optimal, most healthy way to run those containers across multiple different hosts and multiple different machines. And with that, it comes with some really advanced, really cool features. Things like role-based access control. So who is actually responsible and who is allowed to deploy and manage containers running in production? But not just who, but also what context are they working in? Making sure that Team A can't interact or interfere with Team B's containers by mistake. Making sure that you can start defining quotas around what teams are allowed to deploy and how much resources they're allowed to be allocated. And so you could start seeing companies build similar things to like platforms, other services, and cloud-like nature within their own company. And you can say that like Team A is allowed 20 gig of memory and allowed to deploy thousands of applications, while Team B is more constrained because it's a test environment or it's a staging environment. And so they're only allowed a maximum of 2 gig. So if something does go wrong or a process goes rogue, it doesn't take down our cluster. It doesn't interfere or interact with other things running on the system as a host. We see things like auditing, so if you need processes and you need tracking about what's being deployed within your system for like financial regulations, for etc., then Kubernetes is keeping a track and is keeping a list of all the events that are happening. And you can see when versions are being upgraded, when systems are being scaled up and scaled down. Also really helpful from a debugging and just an awareness of what's happening within your system. You can see who did what at what point in time. And there's lots of other features which are amazing. One which I'm a particular fan of is batch execution. Running containers is great. Most applications will be long-lived, there'll be databases or there'll be web servers, and we want them to run, and if we deploy them, we want them to stay running, and that's their aim, and that's their responsibility in life. But sometimes, as we enter into a world of big data, we don't want long-running big data workloads. What we want is short, small, optimized workloads, but we want thousands, hundreds, tens of thousands of them. And we want to be able to run as they manage and process this chunk of data, and when you're done, just simply stop your execution and give up your space to the next process in the queue. And this is what Kubernetes is designed to do. Kubernetes is designed for managing and scheduling workloads. It's not just about long-running web servers. It's about what workloads require execution. And so we can have our big data processes, we can send them to Kubernetes, and Kubernetes will manage what resources are available on our cluster. When a resource becomes available, it will deploy the workload, and when that's finished and the resources are available again, it will deploy the next workload in our system. Really powerful when we start to think about things like GPU and how we can make GPUs available for big data. And GPU will sit there in a server may have 8 of them depending on how passionate we are about our workloads. And Kubernetes will say, like, we can run a maximum of 8 workloads at any one point in time. So we'll allocate those 8. They'll use the GPU however they need. And when they finish, the next workload will be done and will be processed. And we start to build up this queue. And we don't care where it's running. We don't worry about how to make it run and how to allocate that resource explicitly. Instead, we just want to make sure that it's been run at some point in time. So Kubernetes is really advanced and really cool, and this is where Azure fits into the picture. So the Azure Container Service is the new offering from Microsoft, and it's responsible for running containers. But the way it does this is by bootstrapping and deploying clusters like Kubernetes, or Swarm, or DCOS. And it does what Azure is amazing at. So starting machines, making them available, ensuring that they're in the right availability sets, configuring things like load balancers, assigning IP addresses. But it doesn't do any more than that. It then lets Kubernetes do what Kubernetes is awesome at too, which is managing workloads and scheduling workloads and making sure that our containers keep running. And so it's really a best of both worlds. And that's why I'm really excited about why Microsoft is heading in this direction. And so when we deploy Kubernetes on top of Azure, it will tell us and define what the default configuration and setup is that we need. So we need a master, which will manage all of the scheduling and manage all of the health and making sure that what we've asked to run is actually running. And then we'll have nodes or agents running. And they'll actually be the ones which do the workload. They'll be the ones where the container is actually running and is actually executing on. And this is all structured within availability sets. And so we can start adding reliability. If we lose an Azure region, then the container service can cope with that and make sure that that's been defined correctly. And one of the really nice things about running in Azure and running with Kubernetes is it all integrates naturally. It's aware that it's running inside of the Azure data center. And so it knows how to interact and configure things like load balancers. And so we don't have to manually go in and assign IP addresses. We can let the process and let Kubernetes manage that. And that's what we'll see. So there's three current container orchestrations available. Docker Swarm, which is a native default from Docker, which is very good. It's got some really nice features. Got Kubernetes, which obviously is one I'm passionate about, and DCOS, which is awesome, but you need to be at a certain scale, I think, I feel, in order to take maximum advantage of it. And so this is why I think Kubernetes is in the sweet spot between both. Alongside Kubernetes, there's another project which I think is awesome too, called OpenShift. OpenShift is created by Red Hat, and it takes Kubernetes, it's Kubernetes under the covers, but they've added their own opinionated views on top of it, and delivered a cleaner out-the-box experience. And so it will manage things about your entire workload process from start to finish. And so it integrates with Jenkins, so you can start building container images. It will then, from Jenkins integration, it will push it into its own private registry internally, so that's been managed and maintained for you. And then because it's running on top of Kubernetes, it will scale out across multiple nodes, multiple data centers, and keep your application running. And then it comes with all the security, all the routing, everything which you need in order to be able to run effectively. And under the covers, it's just Kubernetes. And a lot of the features which you see, like role-based access control, originally started within OpenShift. And then then Red Hat pushed them upstream and made them available to the rest of the community, which I think is cool. So I'm hoping that that will appear on the Azure Container Service soon. So let's say we want to deploy Kubernetes. Let's say we want to go and we want to use Azure to bootstrap it. And so within the portal, there's the Azure Container Service. And the first option which it asks you is, what do you actually want to deploy? So drop-down menu, select Kubernetes, we're all good to go. The next stage is we need to configure the master. So we need to configure the machine which is responsible for or managing all the workloads within our system. So we give it a DNS name so we can talk to it. We give it the public key of SSH so we can log into it. And then we deliver this strange service principal, which I'm not 100% confident about, but I do know if you run those 4 commands, then it will create you the username and password. And from my understanding, the way this is used is it's used in order to be able to configure the Azure load balancing and configure the Azure environment within Kubernetes and create that barrier and create that integration. With the Azure Cloud Shell, we don't need anything stored. We've got it all within the browser, which is awesome. And so we can take these commands and it will produce the information which we desire. And the next thing which we need before I move on is the master count. So 301, 3, 5, 9 masters, just for reliability purposes. And depending on how large you're managing, you're anticipating your cluster to be, will depend on how many masters you expect. I'd recommend running 3 if you're running across multiple data centers or multiple regions, because if one goes down, if you lose a region, your system will still be up, it will still be healthy, and it will still be managed. But for the purposes of experimentation, 1 master is great, and it will get you there and solve your problem. So the next stage is then configuring the agent. Define how many agents you want, so how many nodes will be processing the workloads, depending on what you've got. So you can start with 1, and you can change it later, which we'll see. Define what machine type or what size, so the standard DS2 machine in Azure, and then what operating system. So for, we'll talk about that in a moment. And then Microsoft and Azure will go off, it will deploy and start all of the machines, which obviously Azure is very good at, and then deploy Kubernetes and configure all and bootstrap all of that commands. And this was all done through the portal, but with the, it's Azure, there's an API for everything, and so we can do it through the command line if we wished. And so by using Azure, going to the ACS and saying create, we give it what type of orchestrator we want, in this case Kubernetes, and that will deploy our cluster. We can then install command line tooling for managing and interacting with the Kubernetes cluster, get the credentials required, and then that's everything we need. And with the Cloud Shell running on the iPhone, we can do that from an iPhone if we want, on our train, on the way into work, and then by the time we get to work, it's all been happily deployed and everything's running for us, which is pretty awesome. So we have our Azure has now bootstrapped Kubernetes for us. And so we can either SSH in based on the public key which we gave it, or if you went through the command line, we'd have installed the client tool, which is called kubectl, and we can remote administrate it from our local machine. Either way, perfectly acceptable and desired. I'd probably recommend downloading it locally, because then you're not SSHing into boxes, but the choice is yours. So the first thing which you can ask is so you bootstrap my cluster, so what are you aware about? And you can say things like Kubernetes get nodes, or kubectl get nodes, and it will list the master, it will list the agents which it's aware of, and what their status is. So are they down, are they being configured, or are they ready to be have workloads deployed on top of them, which in this case they are. So now deploying workloads, and a lot of the complexity about how it operates in the covers has kind of been hidden for us. It's all available and it's all happening under the covers if we want to go low level, but from a high level, we can simply say kubectl run, so very similar to Docker run, give it the name of our deployment and what the project is which we want to run, and the image which we want to be deployed. In this case, our .NET example which we deployed earlier in the presentation, or built earlier in the presentation. And then we can ask Kubernetes certain things about what the state of our cluster and what the state of our deployments are, things like get deployments. So this will list everything which is running on our cluster, and it will list the version numbers, which is why we're seeing the desired and current state, how many of the version or how many of the containers are up to date and running the particular version we want, and how many are available. So we get some insight, and as we start scaling up, we can see what that state is. But under the covers, fundamentally, it's all running containers. That's the process of what Kubernetes is doing. When we say kubectl run, we are scheduling the workload. We're scheduling this image to be deployed inside of our cluster. Kubernetes will then go like, oh, cool, I've got something which I need to do. It will find the most available node, which the workload needs. In the case of this, we've only got one agent or one node, so that's where the workload will be scheduled on. It will then tell that node that it needs to do something, in this case, launch the container. And that's what Kubernetes is managing and wrapping up and making available for us. So now we'll have our container started, but we need to make it available to the outside world. And we do this with kubectl expose. We tell it what deployment we want, the information about ports. So our application is running on port 5000. So we say that all traffic, all of the incoming requests should be targeted toward 5000. But we can say, actually, from the outside viewpoint, we want to hide that. So run everything on port 80. And so when requests come in on port 80, send them to our application, send them to this cluster, and all the traffic should go into port 5000. And finally, we say type load balancer. This means that it will go off to Azure and configure the load balancer for us, define an IP address, make sure that it's all running in a secure nature, and then give us back. So we say get the services. Internally, it will have its own IP address, but you'll see that it's pending, waiting for the load balancer to be configured and waiting for that IP address to be started and allocated. And so after a few moments, the IP address will appear, in this case 40.18.156, and we can now send requests to that. We could update our DNS, we could add a CNAME, and give it a nice pretty URL, and that will now start responding to requests from our application. And this will go to Azure, go to our Kubernetes cluster, go to the most appropriate pod, and that is what will get processed. And now everything, we send more requests, everything will be responded to from our container. But running one process isn't very interesting, so we can now start scaling up and scaling our workloads. So kube could all scale and say we need 3 replicas. We need 3 instances of this application running across our cluster. And under the covers, again, Kubernetes will go, I need to schedule some workloads, find the most available nodes. If we had 3 nodes within our cluster, it would deploy 1 instance onto each in a spread mentality to try and make it as available and available as possible in case we lose that node or an application crashed, for example. And then we'll have 3 pods, 3 containers running, all with their own unique names. And under the covers, this is also updated and configured our load balancer. It's aware of what the state of our cluster is, it's aware of what's running, and it's aware of how we told it to expose our service. And so when we started in this IP address using curl, we'll get round robin to each of the available pods in our system. Now, okay, from a system. And so with these commands, we could take our Azure Container Service, our running Kubernetes cluster, deploy our application with the particular image, expose it and make it available with the Azure load balancer, and then use get service to get that external IP address and find out what's been allocated. Or we could go to the Azure portal. It's all listed and it's already defined in there, and so we can make it available. And now we can start scaling it up and start scaling down our application. But as we're doing this, like we've currently only got 1 agent. So what happens if it goes down? Like how does our system start responding? And the chances are we want more than 1 agent, and we want more than 1 thing in our system. And so through the Azure portal, Azure, as I mentioned, is managing the infrastructure, or Azure is managing and making sure that these machines are available. So we can set the agent count to be whatever we need, and we can scale this up and scale this down as required. So in this case, we're saying we need 2. Once that's been saved, Azure will start spinning up an additional machine. And now it also knows how to configure Kubernetes. So we'll add that new node into the cluster. That node will then get configured and iterated and initialized. And then after 2 minutes or so, we'll have that additional agent available. So it makes it really easy and simplified to add additional workloads and additional effort what we need in order to meet our demands. Once that demand has gone, we can scale it back down again. And so now when in our system, and now we've got this additional agent, we can scale our application, we can say we need 6 replicas, and then it will start issuing that workload. Initially, it will say, like, we've only got 3 available because the image hasn't been downloaded and it hasn't been started yet. But you can see you've got that mixture between what we desire and what we actually have available. After a few moments, once it's been initialized, you'll see everything deployed. The kube will go from 3 to 6, and our system and our load balancers will operate across 2 different versions. So now we've got our application working. What about deploying new versions? And again, Azure and Kubernetes is there to manage this for us. And so in our system, kube could all set image, give it the name of what the deployment we want to be updated, give it the new version of our image, which we want to be deployed, and then Kubernetes will do a rolling update of our application. And so it will make sure that we don't lose capacity, we don't lose any downtime with our deployment. Instead, it will go to each pod and it will replace it. It will stop the previous version, start the new pod, start the new container, and then launch it and make it available in the load balancer. And so as we're doing sending requests, you'll see it being popped and kind of spread across these different versions until it's completely rolled out, until seamlessly from the user's point of view. But what about the Azure registry? At the moment, we just said deploy the one from the public images. So where does the Azure Container Registry come in? And so we need first to tell it about some secrets. We need to give it some username and password so it can go off to the registry and actually get access to our images. And so Kubernetes has all of the secrets management and all of the security built in. And so you're storing in that highly secured way, using command line or using different approaches. But in this case, we can say create a secret of type Docker registry, and this can be our username and password in order to be able to go off and pull our images. Under the covers, as I said, you can use the command line or you can do it the low-level way. By default, this is all based on YAML, and you can see things about how that application is configured and some of the conventions which Kubernetes have put in place. So how many replicas do we need? We're currently at 6, but we could go in and change this up and down. What's the rolling update strategy? So when we say update our image, how should that work and how should that operate? How quickly should we change each image? Should we wait a certain amount of time for the application to start and become available before we move on to the next one? And then we can point it to our image. So our Azure private registry, we can tell it how to access it using image pull secrets, so it knows which authentication and which username and password to use. And then when we deploy this, it will go off to our private registry, but work in exactly the same way that it did before. And Kubernetes now allows us to do some really interesting work, particularly around things like the event loop and managing our deployments. So we've got this YAML, which is the definition in the covers, but this allows us to issue and schedule different types of workloads. So let's say from a monitoring point of view, we have a monitor which needs to be deployed onto every single agent within our cluster so that we can track and monitor things successfully. So now with Kubernetes, we can say this is a type of a daemon set. A daemon set is a container which is deployed onto every single host within our system. And so when in Azure we said added that new agent, the daemon set would have automatically been deployed and automatically been made available within our system. And so we wouldn't have had to explicitly go in and configure and bring up certain workloads. It would have just happened for us based on what Kubernetes is aware of what our desired state should be. And this is where we start getting some really interesting approaches and some really interesting capabilities. We also now have Windows containers. Like we have Linux containers at the beginning, but with Windows Server 2016, we can run Windows containers. Within the Docker file, when they get built, they'll do things like you can define dependencies, but like Windows dependencies, so IIS. We can install Windows features like the ASP.NET framework. We can configure how IIS works and operates. In this case, creating a new website called Nerd Dinner. And just like we did with Linux and Linux containers, we can copy source code in this case, the Nerd Dinner from May 2010, the traditional ASP.NET 2 example application, but we can now build it as a container, completely untouched, completely independent, using the same tooling and same approach, Docker build, but now we're targeting Windows, and we're targeting and configuring a Windows container and Windows functionality, such as IIS. Can be launched and it can be operated, and we have our beautiful ASP.NET application running as containers, but more importantly, it can be operated and it can be worked in exactly the same way. Within Azure, we've got another drop-down saying the operating system, and we can select Windows. And so now our cluster can start operating and working in a hybrid fashion. It can manage our new, shiny, awesome applications built with ASP.NET 2, ASP.NET Core, or Elixir, or anything running on Linux, in exactly the same way it operates and manages our traditional applications, running on things like IIS and ASP.NET 2.0. And having this seamless, transparent experience between the two, and using the same tooling, the same conventions, and the same approaches in order to scale those up and scale those down. And I think that's a really interesting proposition about where this can start heading. And I think this is what we're going to start seeing with containers as we move forward. We already have SQL Server running as a container now. And so we simplified how that looks and how that feels and how we can operate that both in development and production. But what about development time? What about things like Visual Studio as a container? Like, why do we download and install, download 5 gig of the installation files to spend an hour having it set up and configure itself, to then only need another update or override or interact with other Visual Studio installations already on our system, and so we can't work with things side by side? If those operated as a container, they would be completely independent. they wouldn't interact with the registry, and we can run different versions seamlessly side by side without them interacting. And when an update does get applied, we'd simply download the image, download the new layer, and that would what gets run, and that's what gets started. And we're now finally starting to see this come into interaction. So this is Eclipse, the new version of Eclipse, which is significantly better than the old versions, and it's significantly changed about how it gets deployed. When you go onto the Eclipse website, the getting started and the installation is Docker run Eclipse. The entire IDE and the entire installation experience is based around containers. It's based on how we can keep things sandboxed and isolated, but still run in a really interesting desired workflow state. So, just to summarize, we have containers. We have containers which can simplify our deployment process, be it Eclipse or be it SQL Server or something like Redis. We've got this consistent experience about how they can be launched, how they can be built, and how they can be operated. And so we don't need to configure build agents anymore because all of that complexity sits within the Docker file itself. And that's where we define what our application needs and define how our applications are built. Once we start scaling this out, we've got tooling like Kubernetes, which can help manage and scale these applications across multiple different agents, configuring the load balancers as required, making them available, making them secure, and ensuring that if they do crash or if a node goes down, that workload is rescheduled somewhere else to make sure we're not losing availability or capacity. By building this and deploying this on top of Azure, we can take advantage of what Azure is really good at, which is starting and configuring and bootstrapping infrastructure, and then let Kubernetes and our workflow sit on top of that without it having to reinvent the wheel or use different third-party technologies. And then when it comes to things like monitoring, Kubernetes can manage that workload. We can deploy these daemon sets, which get executed across all of our nodes. And so when new things happen and when new agents are deployed, they automatically fit within our monitoring system because automatically they have the right configuration and the right settings being deployed onto them. And so we can monitor our applications across the entire thing. And so with that, I'd like to thank you very much for your time and for attending. I'd love to hear your feedback about if you're playing with Kubernetes and you get started, what you think. How did it work? How did it work for you? And if you have any questions, please do feel free to reach out and send me an email or drop me a tweet or catch me at the drinks later. And with that, thank you very much. I hope you enjoy the rest of the conference.